Hello, welcome to CSE 351, Introduction to Data Science. So this is the first lecture and in which we are going to study one topic from the basics of linear algebra. And this topic is vectors. So the reason we are studying vectors in this course is as follows. So as you all aware, the field of data science have had an exponential growth in recent years, mainly due to having access to millions of terabytes of data. So in order to present this data to machine learning algorithms for the task of prediction or analysis, we need to present this data. And these data are high dimensional. Therefore, we need to use vectors. So there's no place where when you're analyzing the real world problem, you're dealing with scalar. You always use vectors. Another reason is when we are doing implementation, data science algorithms or machine learning algorithms, the implementation these days is all vectorized. As an example, if you have two vectors and you wanted to multiply these two vectors, if you wanted to implement an algorithms in any programming language, so you may want to multiply them element by elements. If you wanted to implement an algorithm, you may use a loop, and then running the loop, multiply the numbers. But in today's tools, there's no place to use loops. All the methods, they are based on vectorizations. That means we convert the data to vector, and then if you wanted to do some operation, we do the operation on vectors. And that's save time for computation, and it's very, very efficient. And also, we know that these days, most of the prediction methods are based on deep learning, and they have devised softwares and also hardwares that are optimized to do the vector operations. So for these two reasons, we need to explore the concept and also the different operations on vectors. I'm pretty much sure if you spend some time to understand vector operation, that would ease the rest of this course, and also it's a tool and it's a concept we are going to use throughout this course. So therefore, pay attention to these topics. Also, at the end of these slides, I have provided the references, 3 references. These are very well-known books. They are available online. You can download them, and also I will upload them on Blackboard. You are welcome to go and study these books if you need further explanation, or you feel that the slides are not self-explanatory. Okay, so with this rather long introduction, let's first see what is a vector. So in order to have a definition for a vector, we should have a distinction between vectors and sets. So sets, which are a topic in math and pure math, is a collection of distinct items. So these items, for instance, we can define a set as X, where X could be a set of distinct items. This item might be shapes like a triangle, like a square, a circle. So The requirement that a collection of items be set is they should be distinct, and they could be anything, any objects. However, a vector is a collection of ordered item. What does it mean to be ordered item? And also finite. That's the two properties of vector that belongs to a vector space. So we can define a vector as, again, x, where x is, we can use some numbers in here, 6, 5, 10. This is a vector. So the terms of order means that this vector is different from this vector, 5, 6, and 10. So as you see, these two vectors, they have the same elements. If you pass them to a set in Python, they are the same, but they are different vectors because a vector is an ordered finite item. So here we have 6 and 5, here we have 5 and 6. So the order matter in vectors. So they are samples, vectors are samples that belongs to a vector space. So now, what is a vector space? A vector space is a set of objects that can multiplied by a scalar and add together. So these are the property that makes a collection of items to be a vector. So for instance, if I define a vector like V as a car and a bike, this is not a vector. This is not a vector, not a vector, for the reason I didn't define how we can multiply this vector by a scalar, right? For instance, if I want to multiply 5 by V, then how can I multiply 5 cars by like a 5 times car? How to do this multiplication? We didn't define this multiplication. So a vector is a collection of ordered items that has two properties. We can do multiply the vector by a scalar, and then we can also add up two vectors. So that might bring you to this conclusion that the vectors is only could be numbers. This is not true, however. If we define a vector space in which we can have a multiplication and also addition, then also that vector space, even though there are not numbers, this is also could be a vector. However, we should first define these two properties. So this is what is a vector and what's the difference between a vector and a set. Vectors notation, how we use vectors in this course, or there are each reference books, if in literatures we are using many different types of notation for vectors, but the most common one is a bold lower case letters usually used for vectors like x. So for here, because I cannot use the bold or not bold, so we consider a lowercase English letter as a vector. So this is how we use a vector. So, and also the collection of items could be in, we usually put it in a square bracket, like the number 5, 10, 16. This is how we define a vector. So this is important because later on we also define matrices. for matrices we use the capital letters, so we want to distinguish between this is a vector. Some other texts also use vectors with an arrow on the top. That's another way of using a vector. So like a 5, 10, and 16. There is also another way to use vectors. So we usually using a block. This block would be a horizontal block or like a column. So we can also have a definition of vectors like this: 5, 10, and 16. This is also particularly important that we know that how we define a vector. It's a horizontal vector or is a column-wise vectors. Why? Because later on we wanted to do multiplication on vectors and then we wanted to do dot product. If the dimension of vectors are not matched, then we are going to have problem. So for now, we use both of these representations, but later on we will define the dimension more specifically such that that is how to do the multiplication. So the reason this topic is important because we are going to implement some vector operations and do some vector operations in NumPy, which is a package in Python. Then when it comes to dimensional vector, so if you want to define what's the dimension of this vector, so this vector dimension is 1, right? Because this is a one-dimensional vector. But however, another way of defining, so the dimension, I can say the dimension of this vector is 1 by 3, right? It's 1 by 3, 1 row and 3 columns, and this vector's dimension, so the dimension of this vector x in here is 3 by 1, right? But when you're in NumPy, vectors usually define as one-dimensional. So this vector dimension is, if you pass it, if you get the x dot shape in Python, that would be 3 by something like this. So that means this is a three-dimensional, one-dimensional vectors. So this have in mind in here later on when you are going to do this operation in Python, make particular attention about the dimensional vectors. So dimensional vector could be one-dimensional, as a, having 3 elements, or could be 3 by 1 when you wanted to introduce it as a matrix. Okay. Okay. More on dimension and type of elements of a vector. So here we wanted to have a notation because we wanted to have not the informal language. We wanted to have a formal language in which we could present a vector, right? And this formal language, or in other words, we want to speak mathematically. So imagine I have this vector x, whose elements are 5.1, 0.001, and minus 5. This is my vector, okay? So if I wanted to have a formal notation to define this vector and the dimension and also type of elements. So I can say this vector dimension is 3, so the dimension is 3, or I can say the dimension is 1 by 3, both are correct. And the type of elements are real. okay, real numbers. So we also use the letter R, the cardinal notation of letter R to denote the real numbers. So as you see, this is a kind of very long sentence, and we have lots of words. In order to have a standard notation, we usually use this notation. So we say x belongs to real numbers, and then the number of elements, n, is, we put it here, 3. That's how we use this notation in order to show a vector. Sorry. Okay. There is also another one. We can say this is a 3-dot vector. This is another notation. The number of elements dash vector. So we can say x is a 3-dash vector. So that means this is a 3-dimension. But throughout this course, we use this notation. Okay. So if I have, let's have another example. Hopefully, this is very simple things. So if I have this vector, let's say, if I have this vector, if I have this vector of y, whose elements are 5, minus 1, 1,000, and 3. Okay, if I wanted to show this vector in a mathematical notation, then I would say, okay, what are the elements of these vectors? The elements are, these elements belong to integer numbers. Yeah, they're integer numbers, and you know that we use the notation of z for integer numbers. So then we say y belongs to set of integer numbers of dimension 1, 2, 3, 4. Okay, so that means y is a vector whose elements are integer numbers, and the number of elements in this vector is 4. And so we know we use the z denotes the sets of integer numbers. Okay, so consider this vector now, vector like m, its elements are 2 over 3, 5 over 6, and minus 1,000 divided by 1,001. So if you wanted to a compact form present this vector show the type of elements and the number of elements, then m belongs to q3, where q denotes the rational number. Q denotes the sets of rational numbers. Okay, so hopefully that explanation is enough in order to know how we can present the dimension of a vector, and also a type of elements in the vectors. Next, about the subvectors. So we always, this is very important topic. So when we have vectors, we wanted to slice a vector, we wanted to get a subvector out of that vector, So we wanted to use a type of notation in order to show how we can get subvectors. So imagine we have a vector x whose elements are 3, 5, 10, 1, 5, 9. And I wanted to have a subvector which are these elements. Okay, so how can I use a notation in order to show these elements? So we usually use subscript in order to get these subvectors. So for this case, first of all, we know that x belongs to integer numbers, z denotes integer numbers, and the number of elements is 1, 2, 3, 4, 5, 6. This is x. Here is a vector belonging to integer numbers, and number of elements is 6. So I wanted to extract a vector subvector, which here I use this notation from elements the 0, 1, from 1, then we use the colon all the way to 1, 2, 3. So that basically is a vector from 5, 10, and 1. So this is the notation we are using in order to get a subvector. So basically, in a general notation, if x is a vector belonging to, say, real numbers, and the dimension of x is n, x I to j means getting the ith elements all the way to j's elements. But if you're using Python, in Python, when we have a vector, let's say this vector in Python, then the indexing start from 0. So this is 0 element, this is the first element, this is second elements, right? So we should be clear upfront what kind of indexing we use. So we in this course we will be consistent with Python notation. Note that the other programming language like MATLAB, they start the index from 1. So, but putting aside the type of programming language, this is the general way we are using a subvector. And if you want to use indexing, if I wanted to get for instance, the fifth elements of this vector, how can I call it? That there are two notation we can use, x5, or more convenient one is x5. By the way, what is the x5, the fifth element of this vector? So if you pass this one, probably the answer is not defined. Why? Because this vector belongs to R3. Okay, but if you want to have x1 is 10, right? So we are using this notation for extracting subvectors, and we are using this notation to extract the ith elements. So therefore xi denotes the ith element, of the vector, right? The ith element of the vector. So subvectors and indexing. The next topic is some special types of vectors. it's very important to know these vectors, and when you call them, then you know what type of vectors you're using. The first types of vectors are unit vectors. So a unit vector is a vector that all of its elements are 0 except one element, and that element is 1. That's a unit vector. So for instance, if I have x belonging to Zn, Z5, and x is defined as 0, 0, 0, 1, and 0. So this is a unit vector. So as you see, all elements are 0 except 1, and then that element should be 1. So this is a unit vector. Okay? So note that if you have a vector like x belongs to, say, R3, and x is equal to 5, 0, 0, x is not a unit vector. Okay? It's not a unique vector. The reason is, yes, all elements but 1 are 0, but this element should be 1. Right? So these unit vectors are extremely important because later on, when we are talking about the how we can project the vectors to unit vectors, and either when we are talking about the orthonormal basis and how we can decompose a general vectors into basis vectors from some space, then we frequently use the name of unit vectors. And so also unit vectors, they have another particular importance. So when we talk about the inner products, in many applications, you wanted to pick one element of a vector, and then let's say you have a vector of dimension 10, and you wanted to extract the 6 elements. So you can use the indexing, but sometimes it's more convenient to use a product of the unit vector and that vector in order to pick that element. So I will show you some examples what are the application of unit vectors. So usually we use the notation of U, so it's not common, so it is not common, but sometime we use the notation U to denote a unit vector. Okay, to denote a unit vector. Okay. So the next type of vectors are one vectors. So the next type of vectors are one vectors. One vectors. So what is a one vector? One vector is a vector whose elements are all 1. The name implies what type of vector it is. So the notation we are using for one vectors is a 1. So usually we use a 1, but this one is bold 1 in order to denote a one vector. So this is F1. So let's say F1 belongs to 5, that means this is a vector, all of elements are 1. So 1, 1, 1. So this is a one vector, right? Sometimes we don't use this 5, we don't specify the dimension of that vector, the dimension of that vector. So, so we use the boldface notation of 1 to note a one vector. So the one vectors is also one vectors. They have lots of applications. In particular, when you wanted to compute the sum of elements of a vector, when you wanted to compute the average of vector, we use a product of one with other elements. So that's extremely useful vector and it has lots of application. So one vector is a vector that all of its elements are 1. Zero vectors also, that's the name is very straightforward to see what is a zero vectors. So basically we don't usually use a specific notation, but we sometimes we use again a bold 0, and that's a vector, all of elements are 0. Please note that sometimes I use a comma between elements in a vector, and sometimes I don't. It's not a convention. I just put a comma because I wanted to don't mess up with the numbers, and then it will be visually more tractable to have these commas. But again, you can also remove these commas and then have a definition of a vector. Okay, so this is zero vectors, and also for instance, not very necessary, but if I wanted to define a vector O, n is a vector that for all I belonging to n, then O of I should be 0, right? So that's a definition for a zero vector. The next vectors are sparse vectors. Sparse vectors. Sparse vectors. Sparse vectors. So sparse vectors are vectors that almost all elements except few ones are 0. So if you want to have it, there is no rule to say, okay, if 5% of elements are non-zero, it's a sparse vector, is 10% or 50%. It depends on different applications. So different applications, the definition for sparse vectors is different. But if you wanted to have some sort of a sense what is a sparse vector, so let's say x is a sparse vector, is a sparse vector. Okay, so let's let n and z denote the number of non-zero elements. Okay, so n z is also in programming we use that. This is a function called nz. Nz is number of non-zero elements, and also assume that x belongs to R n. So what does it mean? That means the dimension of x is n, right? And then we form this ratio of number of non-zero divided by n. If this ratio is small, then we call x is a sparse vector. What we call as a sparse vector. Okay, but as I said, sometimes we consider for my experience that if a vector has like a 5% of elements are non-zero, then we call that vector as a sparse vector. Sparse vectors are extremely important also in many applications. When you are extracting the features, many of the features are zero, and then we can apply more efficient techniques and algorithms when data are sparse. And for instance, if you have a dictionary of words, and then we wanted to see if in a small documents, many of words are zero. So let's say you have a dictionary of 1 million elements, and if you have a text of 200 words, many of the elements of that vector of dictionary are zero. So therefore, this is sparse vector. And also later on, we define sparse matrices. This is similar to sparse vectors. So it's good to understand these type of vectors in here, because we have analogous matrices as the same names. So we learn about sparse vectors, one vector, zero vectors, and that's the most popular vectors. About the unit vectors and Cartesian system, right? So when you were in high school, so basically you're all familiar with the vectors, and we show a vectors in Cartesian system, right? So when we have a vector, we can express this vector in terms of the unit vector. And why this is important? Because as I said, we are interested to have a linear system. As a machine we would like to be linear, because a linear system is an additive system, so the output is very predictable. So we wanted to see, I wanted to start by a very simple example, and then later we will talk about linear systems that is more clear to understand what are the unit vectors, what is the basis vectors in there. So in Cartesian plane, let's consider this Cartesian coordinate, and let's define a vector. These are units, right? So we call them, those days in high school, this unit, this units. This is 1 unit, 2 unit, so this is 1 unit, 2, 3, 4, right? And also we call this one x-axis, and this one y-axis, and this one 1 unit, 2, and 3, right? So if I define a vector, let's say vector S is a vector of 3 and 2, right? So then I have a vector, so I should go 3 units on x-axis, and 2 units on here, and then I can have my vectors. That was way back in high school, we showed a vector like this. So in here, so S is our vector, and whose dimension is 3 and 2, right? So, so simply, when you wanted to define this vector, this is a vector whose coordinate is moving 3 units on x-axis and going 2 units on y, and then we arrive there, right? If I want, so then we can define some unique vector in this coordinate, right? So we can, if I say u of x is the unit vector in this coordinate, and also u of y, this is another unit vector of 0 and 1 in these coordinates, then I can claim that I can express any vectors in this space in terms of these two vectors. How? So imagine S, which is 3 and 2, right? Then I can write down S as 3 times the unit vector of 3 and 0 plus 2 times 0 and 1. This is equal to 3 times u of x plus 2 times du of u sub y, right? So this vector now expressed in terms of unit vectors. So these are scalar, 3 and 2. So therefore, we can express any point in the Cartesian system or Cartesian coordinate in terms of its unit vectors. There are only 2 unit vectors that define in the Cartesian coordinates, and these 2 vectors are ux and uy, right? Ux and uy. So any vectors, well, if I have a vector, let's call this vector m, whose coordinate is a and b, so therefore this vector is equal to a times u of x plus b times u of v, u sub y. So sometimes in some text they also use an arrow on top of ux and u of y, so that's fine. So this is a unit vector, and then any point in this coordinate can be expressed. This idea can be generalized to any other space. So in general, if I have a vector of x belonging to, say, Rn, then I can define the unique vectors and then express these vectors in terms of the unit vectors. So if this vector's elements, let's say if this vector's elements are x is equal to, say, x1, x2, x3, ... xn. To be more specific, we should use this index 0 if you want to be consistent with Python, but we're starting here by index 1. Then I can define the unique vectors for this space such that u1 is a unit vectors belonging to Rn, and u1 is equal to this vector. So it could be horizontal or vertical, doesn't matter. So first element is 1, and all other elements are 0. And also I can define u2 that belongs to Rn again, and u2 is equal to this vector that second element is 1 and all other elements are 0. And then I can define the un, the last elements, that also belongs to real numbers, and un is a vector, all elements are 0 except the last one, right? Then these are the unit vectors in this general space as n-dimensional vectors where we cannot visualize. We can only visualize 3D vectors for more dimensions, and then we cannot. So therefore, so I can write down now x equals to x1 times u1 plus x2 times u2 plus xn times un, right? That's the way we can express it. So this is very important, especially when we are talking about some decomposition. We would like to decompose the vectors to some basis vectors. In here, these basis vectors are unique vectors, but some in other applications, we wanted to have some unique vectors that they have some properties. They're not unique, we call them basis vectors. They have some properties, they're orthogonal, but the concept is the same. This is how we can decompose a vector to other vectors by projecting into the unique vectors or basis vectors. So this is unit vectors in Cartesian, and example of vectors, there are millions of examples to have vectors. I think that's not necessary in here to talk about vectors, but I will start by giving you some simple examples, like when you want to in Google Map. So in it's simple in Google Map, we use the vectors of 2 dimension, right, belonging to R2. So these are the coordinates of x1 and x2, right? Another example, these are popular example, color map. So we usually use vectors of R3, where there are 3 elements, x, 3 elements, they show the RBG colors. So it's like this vector, like this, means the intensity of this. This is the intensity of R, the intensity of B, and the intensity of G. So this another vector. So there are other applications in which we are using vectors. Vectors are used in natural language processing. In natural language processing, there are units that when you have a document, you can map the document to a vector. For instance, you have a document, that document you first of all get rid of all stop words, and then you have words, then you map the words to integers, and then you present that document as a vector. And then we do some sort of one-hot encoding thing that later on we talk when we talk about the deep learning. In application like speech, a frame of speech is a vector. That frame is mapped to another vectors. In audio, in image processing, we usually use vectors and matrices. Anyway, whenever you are dealing with data, the basic block of data are vectors. So next, I'm going to talk about some basic vector operations.